Hello, let's talk about building microservices on the cloud in this session. After you have completed this session, you should understand what are microservices, what to avoid when building microservices, what are the elements of microservices architecture, and why is DevOps so critical while building and deploying microservices. We will see the capabilities offered by Bluemix for developing microservices and also look at case studies of microservices implemented in Bluemix. Microservices is an architectural style in which large, complex software applications are composed of one or more services. Microservices can be deployed independently of one another and are loosely coupled. You need to be able to deploy a single microservice on its own. This loose coupling enables frequent and rapid deployments, therefore getting much needed features and capabilities to our consumers. Each of these microservices focuses on completing one task only and does that one task really well. Microservices can be developed in any programming language. They communicate with each other using language-neutral APIs such as REST, as well as other mechanisms which we will discuss later. Microservices have a bounded context. What do we mean by bounded context is that a particular microservice does not know anything about the underlying implementation of other microservices surrounding it. If for whatever reason a microservice needs to know anything about another microservice, you definitely don't have a bounded context. Microservices need to focus on a unit of work, and as such, they are small. There are no fixed rules on how small a microservice must be. Our focus is on keeping the interface small. And also we want to keep in mind the latency. What that means is when you're decomposing a system into smaller autonomous microservices, we are increasing the number of calls made across network boundaries for the services to handle a request. These calls can be either service-to-service calls or service-to-persistent component calls. Those additional calls can slow down the operating speed of the system, therefore running performance tests to identify the sources of any latency in any of these calls is important. You can use Bluemix monitoring and analytics service for this purpose. Also, microservices should be caching aggressively. You can also add concurrency, especially around service aggregation. Since using the correct tool for the correct job is important, microservices need to be built using the programming language and technology that makes the most sense for the task at hand. Microservices are composed together to form a complex application, and they do not need to be written using the same programming language. In some cases, Java might be the correct language. In others, it might be Python or Node.js. A microservice needs to be treated like an application or product. It should have its own source code management repository and its own delivery pipeline for builds and deployment. A monolithic application is an application where all of the logic runs in a single app server. Typical monolithic applications are large and built by multiple teams, requiring careful orchestration of deployment for every change. We also consider applications monolithic if, while there are multiple API services providing the business logic, but the entire presentation layer is still a single large web app. In both these cases, microservice architecture can provide a good alternative. As you see in this table, Microservice architecture has multiple code bases. It is easier to maintain. We can scale bottlenecked services without having to scale the entire application. Each microservice can be deployed individually with minimal downtime and can be developed in different programming languages as required. Also, let's compare SOA with microservice architecture. Both of these are service architectures as they deal with distributed systems of services communicating over the network. However, the practical results are a little different because the focus of SOA is on reusability and discovery, whereas the focus of microservices is on replacing a single monolithic application with a system that is easier to manage and incrementally evolve. SOA attempts to put these services forward to anybody who wants to use them. Microservices, on the other hand, are created with a much more focused and limited goal in mind, which is acting as a part of a single distributed system. This distributed system is often created by breaking down a large monolithic application, and the intent is that a collection of microservices continue to work together as a single application. Typically, we don't have an ambition to serve multiple systems at the same time. Also, unlike with SOA, microservices often exist implicitly. They are not discovered at runtime and do not require mediation. They are well known to the consumers and therefore do not require service description. This does not mean that some kind of discovery is never present. Some sophisticated microservice systems might apply degrees of service discovery to make them more flexible and more robust. The main point is that such an architectural pattern is not required. A microservice system where all microservices are aware of each other use relatively simple configuration files and can be still an effective solution. Teams can discover what microservices are available for them to use at development time using either a catalog, a registry, or API management tools. In any case, SOA and microservice architecture share many principles, patterns, and a programming model. When beginning new applications, do not demand that microservices be included in them. Microservices attempt to solve problems of scale. When you're starting, your application is tiny. It takes a certain amount of time and effort by a growing number of developers to even approach monolith and therefore the microservice territory. It is important, though, to be aware of when you are approaching monolith status and react before that happens. Microservices cause an explosion of moving parts. Therefore, it's not a good idea to attempt to implement microservices without serious deployment and monitoring automation. You should be able to push a button and get your app deployed. In fact, committing code should get your app deployed through the commit hooks that trigger the delivery pipelines. Microservices often introduce multiple databases, message brokers, data caches, and similar services that all need to be maintained, clustered, and kept in top shape. It really helps if your first attempt at microservices is free from such concerns. A PaaS such as IBM Bluemix or Cloud Foundry enables you to be functional faster and with less headaches than with an infrastructure as a service, providing that your microservices are PaaS friendly. Each new microservices will use resources. Cumulative resource usage may outweigh the benefits of the architecture if you really exceed the number of microservices that your DevOps organization, process, and tooling can handle. Therefore, it is better to be on the side of creating larger microservices and only split them when they end up containing parts with conflicting demands for scaling, lifecycle, or data. So the main point being emphasized here is don't create too many microservices such that your DevOps is not able to handle them. You have to have a good balance. Making them too small will transfer complexity away from the microservices and into the service integration task. And definitely don't share microservices between systems. It is critical to design microservices with the ultimate business objective in mind. This may require teams across organizational boundaries to come together and design the microservices jointly to service a common business purpose. We should design for failure. There are several design patterns that address failure and ensure stability. One is the circuit breaker pattern, which is commonly used to ensure that when there is failure, the failed service does not adversely affect the entire system. This would happen if the volume of calls to the failed service was high, and for each call, we would have to wait for a timeout to occur before moving on. Making the call to the failed service and waiting would use resources that would eventually render the entire system unstable. The circuit breaker pattern behaves just like a circuit breaker in your home's electrical system. It trips to protect you. Calls to a microservice are wrapped in a circuit breaker object. When a service fails, the circuit breaker object allows subsequent calls to the service until a particular threshold of failed attempts is reached. At that point, the circuit breaker for that service trips, and any further calls will be short-circuited and will not result in calls to the failed service. This saves valuable resources and maintains the overall stability of the system. Another design pattern is bulkheads. Just like a ship's hull is composed of several individual watertight bulkheads, so that if one of the bulkheads gets damaged, that failure is limited to that bulkhead alone, as opposed to taking down the entire ship. Similar partitioning approach can be used in software as well to isolate failure to a small portion of the system. The service boundary, that is the microservice itself, serves as a bulkhead to isolate any failures. Breaking out functionality into separate microservices serves to isolate the effect of failure in one microservice. The bulkhead pattern can also be applied within microservices themselves. For example, consider a thread pool being used to reach two existing systems. If one of the existing systems started to experience a slowdown and cause the thread pool to get exhausted, access to the other system would also be affected. Having separate thread pools will ensure that a slowdown in one existing system will exhaust its own thread pool only and not affect access to the other existing system. Now let's move on to decentralized data management. Ideally, you want every microservice to manage its own database. This enables polyglot persistence using different databases and different types of data stores, such as SQL, NoSQL, Graph for the microservices. At the same time, to preserve the ACID nature of a transaction, we may need to have more than one microservice use the same database. So essentially, for practical reasons, to keep the atomicity of a transaction, more than one microservice may end up using the same database. In that case, we need to be careful while sharing a database because the two microservices need to know about each other, and changes in the shared database need to be coordinated between them. In this situation, the two microservices do not have bounded context. In general, the level of sharing between microservices should be limited to make the microservices as loosely coupled as possible. Now let's talk about discoverability. Microservices architecture requires making services reliable and fault tolerant. This implies we should construct microservices in such a way that as the underlying infrastructure is created and destroyed, the services can be reconfigured dynamically with the location of other services that they need to connect to. When the new service instance is created, the rest of the network should be able to find it and start to communicate with it. Services in Cloud Foundry, the open source PaaS on which Bluemix is based, are advertised to the cloud controller to make it aware of the existence of a new service and its availability for provisioning. So this makes discoverability quite easy. Inter-service communication design. When microservices are spread across deployment containers, how do they communicate with each other? They can use synchronous HTTP-based mechanisms such as REST, SOAP, or WebSockets, or they can rely on asynchronous messaging using a message broker. Asynchronous messaging decouples the services from each other, enabling the sending thread to get on with work while the messaging system keeps the messages safe until it can be delivered to the destination. Another advantage of using messaging is that the back-end applications behind the queue can distribute the workload among several clients. Implementing one or more instances of a back-end worker application enables the front-end app to continue its work without the need to wait for the back-end application to complete. Now, how do we deal with complexity? We can do so through testing, monitoring, and DevOps. Testing a complex system requires suites of unit and integration tests and a testing framework that simulates failed or failing components, service degradation, stress testing, and the overall system's behavior over the course of a typical day. In addition to conventional monitoring systems, well-designed services can provide additional health check information using publish, subscribe over a message queue. In this way, information can be collected by the monitoring service, providing rich health and configuration indicators. These indicators can be used to ensure that the service has enough capacity to serve current request volume, and we can compare current performance against expectations. Custom health checks can be registered to gather additional data, and all the information collected can be aggregated and displayed in the monitoring dashboard. Now, going on to DevOps. The operations challenge of keeping microservices up and running means that you really need high-quality DevOps skills embedded within your development team. Let's move on to evolutionary design. Microservices architecture enables such a design approach. The core idea is that you can introduce new features and capabilities in your application by changing a single microservice. You only need to deploy and release the microservices that you have changed. And this change only affects the consumers of that particular microservice. And if the interface has not changed, all consumers will continue to function without any interruption. Because microservices are loosely coupled, they are small and focused and have a bounded context, changes to them can be made rapidly and frequently with minimal risk. The ease of upgradability of a microservice enables evolution. One of the great advantages of microservice architecture is the freedom to make decisions about technology stack and microservice size on a per service basis. It starts by having a clear understanding of the purpose of the microservice in fulfilling the user's experience. Let's use design thinking to scope and identify microservices. Design thinking is a process for envisioning the whole user experience. Rather than focusing on a feature, you instead focus on a user experience, what the person is thinking, doing, and feeling as they have the experience. Design thinking is helpful for scoping work to usable and releasable units of function. Designs make it easier to functionally decompose and identify microservices. Let's choose the implementation stack. In doing so, several considerations need to be considered. They are synchronous versus asynchronous, I/O versus processor, that is CPU-bound services, as well as memory and CPU requirements. In most microservice systems, developers use Node.js for serving web pages due to great affinity of Node.js with client-side JavaScripting running in the browser. Therefore, Node.js is quite popular in developing such microservices. For back-end services, they would use a good CPU-friendly platform like Java or Go and reuse existing system libraries and toolkits. For most teams, more than 2 stacks may not be practical. At the same time, there is always a possibility of trying out a new stack in a new microservice without dragging the rest of the system through costly rework. So there is a lot of flexibility. Let's talk about sizing the microservices. Most sizing exercises revolve around partitioning an existing monolithic application into individual microservices. A good rule is that a microservice should do one thing. For example, one of the following tasks: handle authentication, serve several REST endpoints, serve several web pages. Also, for each microservice, it's important that we separate them through a bounded context so that they are relatively self-sufficient. The good guiding principle is that if a microservice needs to talk to 10 other microservices to complete its task, then the cut was made in an incorrect place. So essentially, the microservices should be quite bound in their context, and there should not be too much of interaction because performance is also a key practical factor. DevOps is required for microservices architecture through its 3 pillars approach, namely automation, standardization, and frequent code releases. The DevOps capabilities facilitate continuous integration and collaborative development. We need to incorporate continuous testing and monitoring to accomplish the fast deployment cycles. Now, looking at microservices governance, since microservices architecture is a practice and can only be successful with the necessary discipline and use of tools, we should look into the concept of decentralized governance. Since that promotes polyglot model regarding the technology stack for supported languages, tools, and data stores. The salient features of microservices are asset reuse, functional isolation, localized scalability, and the ease of maintenance. A microservice team is responsible for all aspects of the service delivery, from build to run to fixes. Other aspects to be considered regarding centralized versus decentralized governance are monitoring, logging, single sign-on, backups, operational metrics, and reporting. One of the major challenges that an enterprise embarking on a microservices journey can encounter is to identify common services across domains and the scope and size of each microservice. Typically, functions necessary for logging have centralized governance. That way, there is consistency regarding the style and content of logging, and the logging is centrally available for any analytics and reporting. Single sign-on is another function that has centralized governance, and typically it is integrated to a form of enterprise-wide directory service. Other system-managed capabilities, such as monitoring and backups, are also part of centralized governance. Information about the monitored units, the frequency of monitors and alerts, as well as reporting any issue and their workloads are all determined and managed centrally. So we can see that certain aspects of microservices architecture ask for decentralized governance, whereas others practically are suited towards a centralized governance model. Let's now look at decentralization of data stores. A typical microservices architecture also decentralizes data store decisions. Whether the reason is best of breed for the workload, or licensing, or just a skills decision, the choice of a data store technology is left up to the microservices team. Now, decentralizing data stores has an implication concerning governance. Managing updates can be quite challenging with multiple data stores, since the network calls increase the risk of a failed update or poorly performing updates. So it is necessary to apply design thinking principles to ensure eventual data consistency for microservices. Next, let's look at testing strategies for microservices. Continuous testing reduces the cost of testing, while at the same time helping the development teams to balance quality and speed. Some of the benefits of continuous testing, as we know, are avoiding unexpected disruption to business, more reliable applications can be delivered, we have proactive problem prevention, we are more effective and have quicker testing patterns, there is less rework involved, and we have efficient and happier team members. Also, the operational costs are much lower. Continuous delivery is also a series of practices designed to ensure that code can be rapidly and safely deployed to production by delivering every change to a production-like environment and making sure that business applications and services function all the time as expected through rigorous automated testing. Because every change is delivered to a staging environment using complete automation, we can have the confidence that the application can be deployed to production with the push of a button when the business is ready. Developing microservices in Bluemix. Let's look at developing microservices using the various cloud services available under the DevOps umbrella in the Bluemix catalog. Delivery pipeline is an important cloud service under DevOps. It enables you to create stages and their corresponding jobs for each phase of deployment of your microservice. It is common to have delivery pipeline delivering to different Bluemix environments. such as development, integration test, system test, and green blue production, along with multiple regions or deployment models such as public Bluemix, dedicated Bluemix, and local Bluemix. DevOps, in addition, provides the following capabilities: agile planning through the track and plan service, a web IDE for us to edit and manage source code, and source control management through Git, GitHub, or Jazz SCM, and allows automated builds and deployments through the delivery pipeline service. In this course, we have included a lab session on continuous integration using DevOps. I would encourage you to go through that lab. Next, let's look at communication. Microservice architecture supports both synchronous and asynchronous communication. Asynchronous communication is to be used in scenarios where one microservice app needs to start one or many microservice apps, but does not want to wait for the action to complete. In such cases, messaging is the best communication mechanism since it's asynchronous. IBM MQ-Lite for Bluemix is a cloud-based messaging service that provides easy-to-use messaging for Bluemix applications. IBM MQ-Lite is administratively light solution for messaging. You can choose which API to use based on your requirements, your system architecture, or your familiarity with a particular technology. You can use MQ-Lite to enable apps that are using different runtimes to communicate with each other using the AMQP protocol, which, as you know, is an open standard app layer protocol for message-oriented middleware, providing us with message orientation, queuing, point-to-point and pub-sub routing, as well as reliability and security. So let's move on to session persistence. When a user visits your app on the cloud and establishes a session, how will you ensure that you maintain the same session on subsequent requests since you have multiple instances of the same app serving these requests? If you're thinking of storing session data in your app server memory and relying on session affinity, that's not a reliable architecture, just because instances of your app need to be able to scale up and down dynamically. And each instance should not contain any data that cannot be recovered. Therefore, for a more dependable architecture, applications on the cloud should persist the session data using an external service. And Bluemix offers you session cache as a service that stores and persists Java HTTP session objects. They are persisting these objects to a remote data grid, which is a general use grid that can store strings and objects. Now, session cache remotely leverages the caching capabilities of the data grid and enables you to store all your session data. This service provides linear scalability, good performance, and fault tolerance of a web app's session data. We are able to use a NoSQL style distributed key value storage via the session cache service, as well as provide the following features such as low latency data access, transactional semantics, dynamic scalability of data and transactions, as well as data replication to prevent data loss during system outages. For other types of applications, you can use the IBM Data Cache cloud service as well to achieve similar session persistence. This is a caching service that supports distributed caching scenarios for web and mobile apps. It again uses a data grid in which you can store key value objects. Bluemix also gives you third-party services such as Redis that can be used for storing session data. Now let's look at logging in Bluemix. All the logs from your app are visible using the Logaggregator component, which is one of the components in the Cloud Foundry architecture on which Bluemix is based. Let's move on to controlling access and visibility of endpoints. Many clients are now offering their APIs and microservices publicly as another way of monetizing their business. Bluemix enables you to expose the routes and endpoints of your services so that they can be accessed by your clients. In some cases, actually, you may not want your microservice endpoints to be publicly visible, or you may simply want to limit access to certain users or apps. In that scenario, IBM API Management Service enables you to catalog and control access to your microservice REST APIs. You can also throttle the number of requests allowed to your microservices by specifying rate limits on the number of calls a client can make to your API. Today, the service does not allow you to not make these endpoints visible. Therefore, you may want to use obscure host names and API keys to restrict the access, or even consider using a software-defined networking third-party service. So let's move on to how we can avoid failures. One of the microservice architectural patterns is to detect a failure condition. Bluemix provides certain services to proactively prevent some of the failure conditions. For example, you can enable Bluemix auto-scaling service to prevent microservice apps from running out of memory or CPU. You can also use MQLite to decouple your microservices so they do not hang when one of the microservices becomes unavailable. Bluemix also provides service monitoring. You can use a service status page, which is status.ng.bluemix.net, to see the current state of your services and information regarding event outages. You can subscribe to a RSS feed and can call this RSS feed to detect error conditions and make corresponding mitigation actions in your app. A useful capability is also to be notified using email or text messages when services become unavailable. Another approach to improve resiliency in your app architecture is to consider including historics as part of your app architecture pattern. Also, you can monitor logs using service for error conditions and send an email notification using SendGrid or text message using the Twilio cloud service. And you can consider using service monitoring and notification services like Pingdom. So there are many options available to you for services monitoring. Let's look at incremental deployment rollouts. We all know that a good approach to avoid failures completely is by completing rolling deployments of new microservices and then evaluating their effect on the overall system. By incrementally providing access to more and more clients and closely monitoring the microservice, you can detect anomalies and revert the deployment. A similar approach to avoiding microservice failures is preventing problems during deployment. You can use a blue-green deployment approach where you have two production environments. The live one is on blue servers, and the new microservice that will replace the existing one is on the green server. The environment should be as identical as possible. After the green server has tested, it becomes a live server by switching traffic to it. So let's now look at versioning. After microservice versions are released into production, client feedback results in new versions of the microservice being made available. Microservice developers are in fact responsible for providing clear direction on microservice versions as they go from beta to production, and also providing notifications when they are sunset. Services listed in the Bluemix catalog typically show if a service is experimental or beta or generally available as part of their metadata. Service versioning is the responsibility of the service provider. The service version of the APIs should be described in the documentation of the service. Bluemix will not surface microservice versions in the user interface. One approach to clearly communicating microservice versioning in Bluemix is to add version identifiers to the microservice. In this session, you learned when to use microservices and when not to use microservices. Also, how to componentize your apps through microservices. How a DevOps approach is critical to building a microservices architecture, and how a DevOps delivery pipeline can help you to develop and manage your microservices. I hope you enjoyed this session. Thank you.